welcome you all to this class on defects in material. So we have prepared the groundwork for finding out the stress and strains around defects. Now, point defects we have considered earlier. Okay. Now we will talk about a line defect. The sum of the line defects, that's the line defect which we know, which exists in material, is we call it as a dislocation. Okay. How do we people come to know that there is a defect like that, the dislocation which is necessary? Okay. How was this concept introduced, okay, by Taylor, okay, Poliani, okay, Oravan? How did they say this concept is necessary? Because earlier in the beginning of the last century, when people had been looking at properties of the material, they find that somehow or the other they are not able to explain some phenomena properly. Okay. What are those phenomena which they were not able to explain? You take a metal, okay. If you are trying to deform this metal, okay, what will be the, because we know that the metal consists of atoms, okay, in different planes. If a deformation has to propagate or the sample has to deform, okay, the strength which is required, critical strength which is required, okay, is if we try to calculate it, okay, it was seen to be equal to that of it was seen to be much lower than the theoretical shear strength, okay, the theoretical fracture strength of the material. Okay. We can calculate, okay, what is the stress which is required. This is called as the Frenkel's model of slip, in which we assume that there are no dislocation which is being present. Okay. That before this concept of dislocation has been put forward, suppose there is one layer of atom and there is another layer of atom which is sitting on top of it, and if this layer of atom has to be moved from one position to another identical position, okay, the stress field is that this has to be moved, it should reach this position which is on top, and then it should come down to an equilibrium position. So moving from here to this position and then coming down, that is essentially, if you look at the stress field, it is going to be essentially a cyclic stress field. Okay. So this we can, anything which is cyclic, we can represent it in terms of sine function. So that is what essentially which has been done. Okay. And we know that whenever we move from one position to another position, we are creating a displacement, and the displacement can be written in terms of tau equals mu into gamma. Gamma is the shear strain and mu is the shear modulus. Okay. If we equate these expressions, this expression and this expression, then we will be able to derive a formula of this type. Okay. This formula, when we take this value of x and in fact this term, there is it's not a correct term, that pi is missing, equals mu b by 2 pi a into sine into x by b. This is how this term should be. X equals b by 4. That's 1. So this will become a maximum value. Okay. And if we take b is equal to a, okay, an assumption we make that they are almost of similar order, then the maximum value of the stress turns out to be, which is required to cause deformation, is turned to be mu by 6, it will be turn out to be. There are some refined calculations which gives values of mu by 10 or mu by 30. Okay. That is the stress which is required for a sample to be deformed. But what has been seen experimentally is that at stresses as low as 10 to the power of minus 4 or 1 in 10 to the power of, that is 10 to the power of minus 4 or 10 to the power of minus 5, okay, of those orders, that's less than 5 or 6 orders, okay, value, we are able to deform the material. That means that there has to be something which is present in the material which should make deformation much easier. Okay. That was the one observation. What was the next observation which was done? We have studied crystal growth, right? Whenever we deform whenever we grow a crystal from either from a vapor phase or from a liquid, if the atoms from the vapor or the liquid has to come and settle down on the surface, and that is how the crystal grows. What is the rate at which it will come and settle? Okay, that one can calculate some rate at which it should form. It was always seen that the rate at which the crystal is growing is always much higher than the rate at which it should grow, because that requires some formation energy for the atom to come. That is, if we have a surface like this, an atom comes and sits onto surface, it has to create some bonds. Okay, some formation energy is required for it to get stick onto it. But it appears as if that if it grows at a much faster rate, that means that formation energy is being reduced. There is some defect which is being present, which is aiding this growth. That is the another reason. The third one was that when we look at the X-ray diffraction, okay, if we assume that the sample is a very flat sample, okay, onto which the X-ray beam is falling onto that sample, okay, it is coming in this direction, okay, because it is a 2D sin theta, Bragg law it has to satisfy, and lambda, okay. And if I put a detector here, some portion of the signal will come and reach this detector, and that we can calculate it. But what was found was that the intensity of the signal which is reaching this detector is turning out to be much higher than what it should be seen. Okay. What could be the reason for that? Later on, one of the possible reasons for that is that if this surface itself, though it surface looks flat, the planes which are responsible for diffraction, if they are bent, then what can happen? If it is a bent, internally there is a bending is going to be there, okay, then a ray from here which also will be, okay, satisfying the Bragg angle, and it will be reaching. A ray from here also will satisfy a Bragg angle, okay, and will be reaching. That means that from a smaller region itself, okay, it is not exactly parallel rays, now other rays are also coming into it, adding to intensity. That means that there may be some bending within the crystals. Then what causes the bending if the crystal is grown a perfect way? That means that some defects have to be present which are causing this sort of bending. Okay. So that is how they decided that the concept of the dislocation was put forward in 1936. Okay. And you know that the other question which comes is that the line defects, when we talk about, are they equilibrium defects? They are not. Okay, that will come to later. But can we have materials which doesn't contain any dislocations? Yes, it is possible. This we call it as whiskers. Small dimension sample which can be produced without any dislocations, but point defects will always be there in the material. Okay? If you take that material,
point defects in bulk material will be more than nanomaterial.
yeah, that we can calculate it differently, how it has to be. Okay? Essentially, that point defects are inherently, if the dimensions are sufficiently large, okay, the point defects in the material lowers the free energy. So that is why they are existing. Whereas dislocations, one can calculate what is its contribution to the configurational entropy, because whenever a point defect is being formed, if you look at it, there is an increase in energy because atom is being removed from that side. But when an atom has been removed, the different configuration which it can assume or different positions it can locate itself, that gives the entropy term. Okay, entropy term is the one which is minimizes the total energy. Okay. So finally, it is between the energy which is required for the defect to be formed and then the configurational entropy. The net one decides whether there is going to be a net increase or decrease. That will decide whether it is an equilibrium defect or not. In the case of vacancies, there is a reduction in energy. In the case of dislocations, essentially one layer of atoms which we are trying to put in, and that layer as such has to be positioned at some particular position. Okay, the energy which is required is high to introduce them, and the configuration, number of possible configurations, if we look at it, they are small. Because of that, the energy turns out to be positive always. This we will look at it from a different angle later when we consider about the stress and strain field around the dislocation. Suppose we assume that the material which does not contain a dislocation, we try to deform it. Then what is the strength which is required? Okay. This plot shows what is going to be the stress in the case of a copper whisker. Okay. You can see that it reaches up to, I think here that scale I will have to change it kg to MPa, which I will do it. I think it is about 600 MPa. You can see that from here, when it reaches to a very high value, a dislocation is generated in the sample. When the dislocation is generated, the load or the stress comes down drastically. Now for the plastic deformation to occur, okay, we require very little stress, correct? So essentially from this you can make out that if dislocation is not there, really the stress which is required to start deformation is very high. Or you can say that the yield stress becomes very high, close to fracture strength it will go. Just before it reaches, some dislocations are introduced, then it becomes much easier. So immediately you find that there is a relief in the stress, and then the dislocation starts moving at a much lower stress. Okay. So I talked about crystal growth. Okay. And what is the proof of a crystal growth? Is that when one looks at the surface of the crystal, one can see some sort of a ledges, which is essentially a circular one. This is associated with essentially a screw dislocation which is being present there. What is the, that is, if a crystal is growing, you assume that in this direction, okay, we are looking at this surface. If a screw dislocation is present, that is from here to here, when you take one round, there is always going to be a ledge which is present, one step which is being present. Okay. This will come to later. Okay. And whenever that sort of a step which is being present on the sample surface, okay, the surface, if you find that there is a step which is going to be there, okay, that is this sort of a step, you assume that the surface is there, this is a step. If an atom has to come and sit on this point, how many bonds which it has to make is some number of bonds. If the same atom comes and sits here, the number of bonds becomes less. That means that at the ledge, it is easy for it to get attached. This is how they grow faster. Okay. Bijus vector defines nothing but a ledge. But even before this concept of dislocation has been put forward even in the 18th century. Okay, that Voltaire has put up this one, that what are the ways in which a defect could be introduced in any material. Okay, one, you take a hollow cylinder, okay, cut out from a sample, you can just make a cut, okay, and then you can get bilateral displacement. That is one type of a defect which we can introduce it. He was looking at it that when a material deforms or failure occurs, what are the ways in which these failures can start. Then another is that this itself can be, we have cut, this has just opened out like this. This is one type of a defect which can occur. Another is that we have cut this sample, but there is a displacement which is going to be in this direction.
These are we intentionally doing?
No, you just listen to me. Then this is another one where is a wedge shape which we can create it, where the wedge goes at this pulled it, this is pulled in, this is one way. This is other way is where it is essentially there is a shift also is given, just not pulling. Okay, these are all the only modes in which you can create a defect in a material. It doesn't matter whatever you consider it. That is, for example, suppose we consider this dislocation. You look at it. This is perfectly a circle which you can see it. This, if I take it like this, I can just leave a cut and leave it. It looks as if it is the same. Another is that because of the cut, something this opens out like this. This is one way it can happen. Okay. Other one is that this itself is like this. There is a step which can be created. So this is also one way in which material failure can start. Another is that this itself is moved, but it is moved displaced inside. This is another defect. One is that it can cut which comes like this it can also happen. That is, this will be like this sort of a thing. That's now you see that these are intersecting and going like this. What is the other way in which it can occur? That this can move like this. This is the way it can happen. One is inside, another is outside. So these are all the only possibilities in which you can introduce a defect. This is something which was done long time back. What is the consequence of it? When idea about crystal structure or fracture, none of these things were known. The consequence of it is that with respect to the lattice geometry, some of them are consistent with it. Okay, that is essentially what is beauty of this. Okay, this is the concept which has been used to define a dislocation in the material. Okay, this is essentially another one which was done by Nye and Bragg. Okay, way back in 1947. This is using a soap bubble. They create a bubble and it's a two-dimensional surface it generates. When it generates two-dimensional surface, can there be any defects which is being present in this? Can you locate a defect here in this? If you look at it, it looks, everything looks all right, but there is somewhere a defect is there. Okay, I'll just show you. Around this region now, if you look at it, with respect to atoms, there is a displacement is going to be there, correct? Okay. This is the type of a defect which was proposed as a defect which is present in the sample. Okay. Here what is it being shown? This is shown for an edge dislocation. What is that? Is suppose we have a perfect lattice into which we make a cut. Okay. That is, we take a perfect sample. Okay. Make a slit up to this point, pull it apart, okay. Then introduce on the region which has been pulled apart, add one more layer. then the whole thing will be to the. If you look from here to here, this is a perfect lattice because all layers are, because the separation between them is again here the same lattice translation vector, okay, and here also it's going to be there. But if we go from here to here, what do we see? At this particular point, there is going to be an extra layer which is coming into that. So that one which separates between these two layers where the extra plane is ending, this defect is like it goes like a line from one end of the sample to the other end. This is called as the edge dislocation. Okay. Similarly, here what is it being done? You take the material which is, because I take a circle around it, perfect one, okay. Then if I move it like this, that is essentially after making a cut here along this line up to some point, then that portion I try to shift it by a lattice translation vector and then try to join them. So if you look everywhere, the atoms are going to be joined, except it's going to be there at that point. So this is one way to look at a dislocation defect. Okay. There's a defect which is being present, but far away from the defect, if you try to look at it, all atoms are in lattice position, but there is one point along the center, the defect is being, that is why this is called as a line defect. Okay. These are all the two models which has been put forward. Clear? Okay. This is a simple edge dislocation model was put for a cubic crystal. How are these defects created? This is a way of looking at how these defects could have been created. We assume that this is a model which is a explanation. What is the reason for these defects to form? During the growth itself they do take place. Okay. That is because there are thermal vibrations which are associated with the atoms which are being present. When they come and get attached, the thermal vibrations can cause, finally they arrange into some sequence, suddenly you remove the vibration, lower. It will all be trying to settle down into some position. Now suddenly you find that some region there is a mismatch which has come. That mismatch is what is this type of defects which are going to be there, screw dislocation or an edge dislocation. But how can we think of this one? This is one way we can think of that this is how these defects have formed. Okay. So there are two types of defects which we see. One in which in this, if you try to look at it, what is the line direction here? Okay. The dislocation line is going from one side to the other side of it. Okay. And the defect which has been introduced here also, if you look at it, the step is coming in the same direction as that of the line direction. So these are called as screw dislocations. Okay. This is something like if you take a screw, I try to rotate one rotation, I move one pitch forward. Okay. If I go again, I will go forward. Like that it happens now. So from here to here, if I try to move from here, rotate it like this and try to reach here, I come down. One pitch has happened. So that's why this is called as a screw dislocation. Yeah, that step will come. So this is called as a screw dislocation. Here what it happens, here if I go from here to here, suddenly I find that there's a step which is going to be there in the perpendicular one, in this direction, correct? An extra plane which has been added. So these are called as an edge dislocation. That is, if I take a circuit like this, it is not a step which is going perpendicular to this screen, it is in the lateral direction. So that is called as an edge dislocation. Okay. what are the ways in which these dislocations have been observed, or what are the modes of experimental observation, or what are the results concerning the experimental observation of dislocation. One, electron microscopy, we can use it to observe dislocations. X-ray imaging can be used to observe dislocations. This is one example where with X-ray one can find dislocations in the material. TEM we can use it. Okay. Then another is in electron microscopy, I taught earlier with Moire fringes. Okay. We can generate something which looks like a, this if you like here as well as here. Okay. This looks like a, the way we have seen from the lattice structure, how the dislocation looks like, edge dislocation. Another is using atom probe also, one can see some extra planes like here to here. If you see, there is an extra plane which comes in this region. This is an indication that there's a dislocation which is being present. So all these regions, if you look at it where which are being circled, in that region if you look at it, there will be some extra layer of this bright atoms will be coming. Okay. This is one example, that's using atom probe we can do it. Okay. Now let us come to definition of the Burgers vector of a dislocation. Okay. This is what a procedure is called as a Frank's procedure. Okay. Now we had just got a model of how to model a dislocation. Okay. Now the next question which comes at, how do you define the Burgers vector of a dislocation? To define the Burgers vector of a dislocation, what is it which we do? For any which one, for any work which we do, if we have to quantify it, we should choose a coordinate system. So what is the coordinate system which is being chosen here? Is that the extra plane, that is, which is the plane in which this extra plane is lying, okay, that is from this plane to this plane, correct? So in this direction, this is chosen as the x direction, perpendicular to that, and normal to that is chosen as the y direction, and the direction in which the dislocation is going, okay, that is chosen as the z direction. In this specific case, the positive sense of the dislocation or the z direction is going into the screen. Okay. So the coordinate system which is chosen here is x, y, z is in this direction into the screen. Okay. And that's how it is defined. Suppose we start from any position, yes, we move around it, and 1, 2, 3, 4 lattice translation vectors we have moved, we reach this position, then move some distance around it here, okay, then move by the same distance back here, okay, then move back, then we can come to a point where the finish point, we have come to a identical point, but we have taken a path, or we have traveled along around the dislocation line and reached the starting point, we have completed. Now we choose a region of the sample which does not contain any dislocation. I do identical displacements. If I do that, then you will find that here it is only 4 steps which are required in the negative x direction to reach starting point. Here when you take the 4th step, you find that from the starting point to the, that is finish point to a starting point, there is a gap. Okay. This is defined as the Burgers vector of the dislocation. Okay. This Burgers vector B is always is a negative one, correct? Because with respect to a coordinate system which we have defined, okay, this is the positive x direction, but the step is from finish to start, it comes, this vector is in this direction. Okay. This is a convention which is used to define, to find out the Burgers vector. So what is important is first coordinate system, X is this one, Y is in this one, Z is going into the line sense of the dislocation is going into the paper or to the board. Okay. Then the bias vector B will be defined in this way. This is called as the finish to start right hand convention, because what is being done is that here we are doing a right hand screw, that is this is the direction in which we are moving around, na? Right, like a right hand screw we are trying to do that. This is right. Okay. This is some books it is defined and used this way. There is another convention which people follow. Other convention is that if I take, no, this is like this, other option, X, Y, you take the line sense of the dislocation coming out of the sample, and instead of taking a bias circuit with right hand screw, you take the left hand screw, that is go in this direction and try to come back. This one can do it as an exercise. Then one will find that the finish to start will be in the finish will come here, start will come here. That becomes, that sign changes, it becomes positive. Okay. Both the conventions are being used by different people. Okay. One has to always define the convention and use it accordingly. While reading books, quite often this can lead to some sign changes in the expressions that normally arises because of this sort of the way the convention which they follow to define the bias vector of the dislocation. Okay. Is it clear? That is essentially what we have taken here. What we have done here is that we first do a bias circuit around the dislocation, okay, and then take a region which is doesn't contain any dislocation, do a similar procedure and try to find out what is going to be the gap which is going to be there and in which direction, magnitude of the gap, and when you point out the direction, that defines a vector. And generally in all the crystals this is going to be the lattice translation vector. Dislocations which exhibit, okay, where the bias vector or lattice translation vector, we call them as perfect dislocations. Okay. Here I am just trying to show a comparison. Okay. It appears that if I try to do a bias circuit around a real crystal, that is in a region which does not contain any dislocation, and then I do the same bias circuit around the core, that is around the region which contains the dislocation, then also we can define the bias vector, correct? In this definition, okay, that is from the start to finish is how the bias vector is being defined. But normally we do not use that, because suppose I start from here and try to come back, from here to here this distance near the core, the atoms are displaced from their lattice sites, correct? So it is not a perfect value of the lattice translation vector, which could be slightly different. So if you use this convention to measure the bias vector, it may not be a lattice translation vector, so this convention is never used. The convention which one has to follow is only this one. That is, first you take a right hand screw that circuit around the dislocation, and then do it on a region of the crystal which does not contain a dislocation, and find out the direction in which the bias vector is there. The magnitude also is defined now in a perfect lattice. Okay. Okay. this so far we talked about is with respect to an edge dislocation. How do we go about and do it with respect to a screw dislocation? So similar budget circuit, if we can take it, start from any region, take the right hand convention. This is what I am showing it with respect to a right hand convention. The line sense you can see that is in the direction. This is X and this is Y. Now you see that after this we have come back to original position, right, starting point. The same thing when we do it around here in the perfect lattice, we make every step. Now we find that there is going to be a gap which is going to come. Okay. So this is defined as the bias vector. Is it clear? So what is essentially important is that in the case of an edge dislocation, if this is the line direction of the dislocation, okay, this is the line direction, this is the bias vector. Bias vector is, that is if the line direction we define as u, okay, B is the bias vector, u equals line direction. Line direction and bias vectors make an angle of 90 degree, correct? What happens in this case of a screw dislocation? U and B are in same direction. For this is a screw dislocation. Whereas U and B are perpendicular to each other for edge dislocation. Correct? So this is something which one has to understand. And if a dislocation has to move, how is the slip plane defined? Slip plane or sometimes it is called as a glide plane, okay, defined by U cross B. The cross product is what it is going to define that plane. Okay. So if you are taking the cross product, this is nothing but this is the plane which is going to, if this is U and this is B, this is the plane, correct? Cross B. That's the plane in which the dislocation will move. So an edge dislocation will move only in that plane. Okay. Let us, what is going to be U cross B? And if you try to find out, it doesn't define a plane, correct? Because U and B are in the same direction. That means that no slip plane is defined for an screw dislocation. That means that if a screw dislocation is there, that is any plane around this, that is if a screw dislocation is there, either this plane or this plane, any of these planes which are cutting through that, all of them could be, all of them are potential slip planes for screw dislocation. Okay. But then the question comes is that which is the plane in which finally the dislocation will move. That is determined by in which plane, if the dislocation has to move, the frictional stress is less. Okay. That is, suppose in this particular plane, you assume that the atoms are all densely packed, then the roughness will be less, right? That's the plane on which it can move very easily. Whereas if some other plane, if it is going to be very rough, okay, in that plane, it will not be able to move very easily, or the energy which is required is going to be very high. It is something like this one. If you are driving a riding a cycle on a road, and the road is quite bumpy, okay, because lots of stones or big stones are being put. Then with the energy which you put in, okay, lot of energy is required to go on that road because of, and the road which is smooth, the same energy you can go it very easily. So that's the one which you would prefer to go. Exactly like that, the dislocation also chooses that one which requires less energy to move. So those are all the ones which are chosen, the slip plane. But what is the one condition is that whichever plane in which the dislocation moves, that the line direction will be lying in that plane, okay. But it is, so it's possible that if there is an obstruction to a motion of the dislocation in that plane, okay, since slip plane is not defined, it can try to climb into any other plane in which the Burgess vector is lying, in which the Burgess vector of the line direction is lying. That means that suppose a dislocation is moving in this plane, a screw dislocation moves in this plane, it sees an obstruction. Then if there is another plane which is there, it will try to climb onto it. Suppose this plane also has got a lower, the energy which is required is the same as that of this plane, it will just cross slip. That is why we normally say that the screw dislocations, it is easy to cross slip, whereas for edge dislocation, the cross slip is going to be very difficult. This we will come back to this aspect of it when we talk about specific dislocations in different type of crystal systems, okay. But at this stage what one has to understand is that for edge dislocation the slip line is defined, okay, it is given by the cross product, and by the same cross product if we take it for screw dislocation the slip line is not defined. So any plane which contains the line direction, it is a potential slip plane for the dislocation, okay, that is clear, okay. Then what are the types of dislocations which we can have? We have considered a screw dislocation, we have considered an edge dislocation, okay. There is another type of dislocation which can occur, which we call it as a Frenkel dislocations, okay, or these are also called by the name prismatic dislocations. How can they form? Suppose we take a sample, okay, we take it to very high temperature, okay, lots of point defects are produced in the sample, we quench it to room temperature. This happens most of the time in the case of aluminum samples, it has been seen. In the quenched sample, these point defects, if they are able to move at some particular temperature, they can agglomerate together on some particular plane. If they agglomerate together on a particular plane, what will happen is, this is the sort of a structure it will be formed, because one set of atoms are missing, this is equivalent to point defects which are generated, right. This is only a cross section which we are showing it. If you look at it everywhere, there is one extra plane has come on this side of it, an extra plane has come on this side of it, in between there is nothing is there, right. This is a three-dimensional view of it. From this you can make out that the Burgess vector is always going to be in this direction. The direction in which this defect is lying is in this particular one, Burgess vector is perpendicular to it, but this is not the slip plane, okay. This type of defects are called as the Frenkel defect. For this particular defect, if we try to find out the this is the direction of B, and if we consider this as the closed packed plane, okay, and the line direction will be, this is essentially a sort of a loop which is being formed, because one defect layer is there, we are only seeing a cross section of the cut section, okay. So the line direction will be a circle which is going around. If you look at it in the perpendicular direction from the top, if we see it, it will be like a, this is the line direction, okay, and the bias vector is perpendicular to it like this, it will be there, okay. Bias vector and line direction are perpendicular to each other, okay. That is the one which defines the slip line. That means that if it slips, it has to move in this direction, right. That is on a cylinder it moves. Is it clear? So these type of defects are called as Frank loops or Frank dislocation or prismatic dislocation. The same thing can happen in another way, that instead of vacancies, it could be point defects which can agglomerate in a plane, okay, like what is being shown in this particular case. This also gives rise to the same type of a defect. So this is called as a vacancy type of a loop. This is called as an interstitial type of a loop, okay. But both of them create dislocations, okay. Then there is another type of loop which we can have, which is called as a shear loop. I will talk about it, why this loop which it forms is that whenever we talked about a dislocation, right, but we never mentioned where is it starting. We said that some dislocation is there, some cut surface we are looking at it. Where it starts and where it ends, that is very important. The dislocation can never start within the center of the sample. It has to always be from outside. That is, dislocation can never begin nor end within a material. It has to be only from surface to surface. It will be moving from one surface to another surface. The dislocation line will extend. That is the first thing which you have to consider it. This you can do it as an exercise. You assume that a dislocation is ending within the bulk. Then you try to look at it, what sort of if you try to view it, you will be able to make out that it generates another dislocation in some other direction, essentially indicating that it just cannot end within the material. So in a polycrystalline material, what happens is that the dislocation begins, okay, and ends, okay, from one end of the grain to the another end of from the boundary. That is, so that dislocation cannot stop within the material. Okay. This is one thing which one should always remember. Okay. So far we talked about a dislocation which is essentially either a edge or a screw dislocation. But there is no need that the dislocation line has to be, that is when it is perpendicular, that bias vector and the line direction are perpendicular, we call it as an edge. When the bias vector and the line direction are in the same direction, we call it as a screw. It can happen in so many cases, a dislocation line which we see it, but the bias vector is going to be in this direction. Like here also bias vector is in this direction. So if you see it, the line direction, this is the line direction. So here the line direction bias vector is in the same direction. There can be some other position, it could be inclined. So these type of dislocations are called as mixed dislocations. This is the type of dislocation which we normally see in most of the material. It is only the mixed dislocation which we see. Is it possible pure edge dislocation? Yes, under some conditions they do form in materials. It is not that they do not. Edge dislocation, screw dislocations form. Perfect screw can be seen, but most of the dislocations are of mixed character. So if it is of a mixed character, okay, if we know the bias vector, if we know, because that is the lattice translation vector, and if this line direction here is u, I can find out the component of this bias vector in this direction as well as perpendicular to it. This is I will call it as BS and this will call it as BE. These two define the component of the bias vector, correct? BS is essentially the screw component of the mixed dislocation and BE is the edge component of the dislocation, mixed dislocation. Okay. So, now what we have done it is that to find out get any information about the mixed dislocation, we can split them into screw and an edge component, okay, and that way we can do a calculation to find out the stress and strain fields associated with it, and then combine them together we get the total stress and strain field, okay, to tackle the problem associated with a mixed dislocation. Okay. How are these dislocations defined? Okay. That is what essentially is being shown here, because in this figure if you consider psi is used to define the line direction, okay, and bias vector, this is the component of bias vector in the line direction, this is the one which is perpendicular to it. When we have to define these can be written in terms of if we know the angle theta between them, the line direction and the bias vector, okay, that is if this is u, this is the bias vector, we can find out the component which is going to be there in this direction if we know the angle, okay. This will be B cos theta will be the screw component, will be B sin theta, correct? That will be the edge component. That is a simple way in which we can write it. But in a vector notation if we wanted to write it, it is a little bit more complicated, okay. In a vector notation if we write it, this we will write it as B will be equal to BS plus BE, correct? This is how we will write it. And the definition of BS is equal to that is what we are considering it is B dot U, that is if bias vector is inclined you find out the component of it in this going to be there. What is the component of this which is going to be there in this one is B dot U. U is a unit vector line direction. So that gives the value. That multiplied by the unit vector in that direction will give you as a vector, na? So that is how you define it. Okay. Similarly, we have to define it for a edge dislocation also. Okay. What is it done in the case of an edge dislocation? Okay. In the case of an edge dislocation, it's a little bit complicated, but it's not very difficult. B cross U, if you take it, what it will decide? This is B, this is U, it will be perpendicular to it. Okay? That is how we define that. Okay? And if we divide by B cross U, what it will give? A unit vector which is going to be there in that direction, right? But what does B cross U actually mean? It's essentially, if U is a unit translation vector, it is B sin theta, correct? That will be nothing but a vector which is perpendicular to it, correct? But essentially what we have to find out is that you take a B cross U, that gives a magnitude B sin theta, take a dot product with respect to E, which is B cross U divided by that unit vector, that gives you a constant value, that is what this expression gives, okay. Then multiply it by, this is the line direction, okay. this is the vector E is a vector which is perpendicular to it, okay, that is perpendicular to it, out of the plane of this paper, okay, and its dot product, its cross product will be perpendicular in this direction, that is the vector. So, you take the magnitude and take the vector in this direction, that will define Bijus vector of the edge component. Okay, that is how it is being defined. But otherwise it is a very simple one, but when you have to define it vectorially, this is the way it has to be done. Okay. Then another thing also is that which we have to consider is, so far we consider dislocations as something which is static. But what normally happens is that the dislocations are the one which, the movement of those dislocations is the one which is responsible for deformation of the material or slip to take place in the material. Okay. How does a slip take place? Let us look at it here. That is, in this sample there is one dislocation which is being present here. Okay. If you look here, 1, 2, 3, 4, 5 layers are here, correct? Top also 5 layers are there. What is essentially being done is that with respect to a bottom, the top layer has been applied some stress so that it is pushed, so that it has just the bottom layer, that layer at the back maintains a continuity. So, this layer has been pushed by one lattice translation vector. Then it has to introduce some defect within the material. This is what a edge dislocation is now around this. When I apply a shear stress, what it will happen is that if by some means, okay, if, because I am trying to push this into this side, then this atom will come, instead of it, this atom will come closer to here. If this joins together, then this will become, that is what is being shown. You see that this one has 1 and 2 are joined, then the 3 has now become the extra plane. Then again another push, that is 1 and this and the 3 will join together, this has come here. When this and these 2 join together, a strap has been created. Now in between this region, if you look at it, there is no dislocation, right? Now a perfect plane which is being maintained. This is the way a dislocation moves. But finally, how many bonds are being broken? Only at this region a bond breaking is taking place, correct, at a time. So that way, breaking a bond here and joining it, breaking a bond here and joining it, this way it is able to move. This is equivalent to, okay, the case which we considered initially started with, if there are no dislocations are there, if by one lattice translation vector we have to move one layer over on top of the other, the entire layer has to be, that is from here, this has to be moved entirely by one lattice translation vector here like this, correct? That need not be done. Suppose this has to be done, what will be the energy which will be required? It will be very high. We can take an example of it. You see this room, a carpet has been put here, okay. Suppose I will have to move this carpet, okay, from here to some step which I will have to move it. What is the way which I can move it? I can hold that end and just pull it. Will this carpet move? If I just hold it to that, pull it, because what is the total frictional energy, how much, this whole total area it has to cover, that is going to be very large. It is not very easy. Instead, what is the way in which I can make it move? At one end of it, I introduce a rod. Just I roll the rod and bring it to the other end, this carpet would have moved. That is equivalent to only that point is being lifted and pulled down, lifted and pulled down. Energy is being spent only there, the rest of the region remains the same. By doing that with less energy, we can move this carpet. Exactly like that, it happens of one layer of atom, it's like a carpet sitting on another layer of atom. By means of having a dislocation, just moving that step to move one at a time, or breaking of bond and joining of bond, we can make the whole layer to move. This is how a dislocation moves. That is why the energy which is required is extremely small also, okay, when a dislocation is present. So when this dislocation moves like this, if we look at it, initially we started, and you can see that there are some steps which are created on the sample surface on the cross section, which was otherwise when the dislocations were inside the material, it looks like a perfect cube. Now after the dislocations have come out of it, shape has changed. Okay. If dislocations are randomly distributed within the sample and they come out on both the directions, a shape deformation takes place. That's how plastic deformation of a material, we now correlate it to the moment of dislocations, okay, and they can bring about shape change. The same if we consider it here, what happens is that in this, when we show a dislocation with this sign, especially this is valid only for a H dislocation. This sign represents when we put, this is an extra plane on the top. If we put it like this, we mean that extra plane at the bottom. This is only valid for an edge dislocation. Generally for screw dislocation also, as a general symbol for a dislocation, we use it like this. That is just to say that it's a dislocation. But now we cannot say that the screw dislocation there is any extra plane. Okay. But this symbol is often used. Okay. Now if you look here, if an edge dislocation is there with respect to this diagram, when the dislocation line from here to here moves like this, the step is also created in the same direction, right? That means that here if you see it, when the dislocation moves, what is the direction in which the step is created? In the direction in which the dislocation is moving. That is perpendicular to the dislocation line direction, in the same direction as the dislocation, but the direction of movement of dislocation is in this direction, the step is created perpendicular to it. Okay? This is what it happens. In the case of a prismatic loop, what will happen? Here you can see that we saw that the bias vector is in this direction, slip line is a cylinder. So finally, if this dislocation comes out of the sample surface, it will be creating this sort of a.
It will always come to surface.
Which one? Yeah. If or it has to go to a grain boundary. If it considers single crystal, it has to come to a surface only. If it moves, correct? And similarly, we can consider as a shear loop. In this, when the loop moves, okay, the shear loop, if you consider it, a loop like this, the bias vector is always in the direction, but the line direction is always, the line direction moves in the same direction, the sense, okay, it has to be continuous. So here, the dislocation will have an edge character, will have a screw character. Here the line direction and the bias vector are perpendicular, it will be an edge character. In these regions, it will have a mixed character, okay.
It needs some time to move the dislocation.
Yeah, that takes finite time. What we are talking about, it is not about the intermediate step. When the dislocation has completely moved and come out of the sample surface, what will be the shape change which we will be seeing it. Suppose a dislocation moves in a sample from this region to this region, okay, no external shape change will take place. The external shape change will take place only when this dislocation has moved and come out of the sample surface. Then this sample will look like a step which might have been created, shape change has happened. We assume there was only one dislocation which was there, it has just come out of it. That dislocation has created a step. With that, its job is over, okay, because the dislocation has vanished from the sample also.
So
Yeah.
what we see means
Okay, so dislocations are generated, they come out of the sample surface, and yeah, and generate some shape change to the sample. So if the dislocations don't come out of the sample surface, no shape change will occur. But when they move inside the sample surface, the stress and strains at different regions will change within that sample. That's what it will happen. This we will talk about it later.